Welcome back from spring break, Bulldogs. It is Monday, April 20th, and today we are going to start a new chapter, Chapter 7. In this chapter, we are going to be learning about specific types of quadrilaterals and properties associated with them. We will be using congruent triangles to help us prove those specific properties of the quadrilaterals we are learning about. In today's lesson, we are going to cover 3 different topics. First topic we're going to talk about are isosceles triangles. We are going to discover some properties of isosceles triangles using properties of reflections and congruent figures. These ideas will then lead us into the next topic that we're going to talk about today, which is properties of parallelograms. We will be using congruent triangles to help us prove some of the properties we are going to learn about today. The third topic we will talk about today are midpoints. Understanding what a midpoint is and how to find the midpoint of a segment on a coordinate plane will also be helpful to us in discovering and understanding certain properties of these quadrilaterals we will be studying. So we'll talk a little bit more about what a midpoint is, how we can find the midpoint of a segment on a coordinate plane, and then we will apply that to parallelograms and specific types of parallelograms to help us discover some different properties of those figures. We will wrap up the lesson today with some guided practice. You will notice at the end there are some problems that I'm going to have you work through, and then we will check your work together. So let's get started. Once again, in this chapter, we will be using what we know about triangle congruency to prove various properties about polygons, specifically quadrilaterals. Let's just review what we learned about regular polygons in Chapter 8. A regular polygon is a closed figure, meaning it has no holes. All of the sides connect, and it's made up of segments, meaning no curves, in which all of the sides are congruent and all of the angles have equal measure. And I've included some examples there of regular polygons you have seen before. In the following problems, we're going to be using what we know about congruent figures and symmetry to discover some properties of isosceles triangles and parallelograms. First, let's start with properties of isosceles triangles. What I'd like you to do is grab some colored pencils, markers, or crayons for this section of your notes. Specifically, we're going to be using red and blue and green. The first thing I'd like you to do is outline triangle XYZ below in red. This triangle XYZ was reflected across side XZ to form triangle XY prime Z. We are going to outline this new triangle, the reflected image, XY prime Z, in blue. So what happened is the red triangle reflected over the dashed line in the center, XZ, to form the blue triangle on the right. In Chapter 1, we learned that when a reflection occurs, the pre-image and the image are congruent to each other. So, if triangle XYZ is the pre-image and XY prime Z is the image, what can we conclude about them? Well, if pre-images and images are congruent, we know that triangle XYZ must be congruent to triangle XY prime Z. Once we know that two figures are congruent, we can conclude that all corresponding parts between the two figures are congruent. So what we're going to do is we're going to make a list right now of the parts of triangle XYZ and triangle XY prime Z that must be congruent. I'd like you to stop the video, make your list, and then we'll come back together and discuss. Okay, we're back now, so let's talk through the congruent parts of the red triangle XYZ and the blue triangle XY prime Z. Let's start with the angles that would be congruent. We know that angle Y must be congruent to angle Y prime. We would also know that angle YXZ would have to be congruent to angle Y prime XZ. And we would know that our two right angles, angle YZX, would have to be congruent to angle Y prime ZX. And of course, these statements are all true because the red triangle and the blue triangle are congruent to each other. If we look at the side lengths, because the triangles are congruent, we would know that segment YX would have to be congruent to segment Y prime X. We would know that segment YZ would have to be congruent to segment Y prime Z. And we would know that segment XZ would be congruent to itself because it is shared in both triangles. In this chapter, the idea that corresponding parts of congruent figures are congruent will be used often in proofs. Now that we have our list of congruent parts between triangle XYZ and triangle XY prime Z, because of the idea that corresponding parts of congruent figures are congruent, let's take a look at the larger triangle XYY prime. We're going to outline that triangle in green. This triangle, XYY prime, was formed when we took the original red triangle, reflected it over side XZ, and created our blue triangle. What type of triangle would triangle XYY prime be? Well, remember, we talked about different pairs of congruent corresponding parts. And one pair of congruent corresponding parts was segment XY and segment XY prime. Because those two sides are congruent, we can say that triangle XYY prime is isosceles. We know this because segment XY was congruent to segment XY prime by corresponding parts of congruent figures being congruent. What we're going to do now is we're going to use the properties of reflections and what we know about corresponding parts of congruent figures to list properties of isosceles triangles. Think back to the list we generated on the previous page of your notes. We said that angle XYZ would have to be congruent to angle XY prime Z because of corresponding parts of congruent figures being congruent. Because these two angles are congruent, we know the property of isosceles triangles that states the angles opposite the congruent sides in an isosceles triangle must be congruent. Now that we are familiar with this idea of corresponding parts and congruent figures being congruent, let's move on to learning some properties of parallelograms. First, plot and connect the points A, B, C, and D to form quadrilateral ABCD on the graph below. Parallelograms are quadrilaterals whose opposite sides are parallel. How can we verify that this figure meets this condition? Well, if we are going to show on a coordinate plane that opposite sides in a figure are parallel, we need to be thinking about slope. Segments or lines that are parallel have the same slope. Let's take a look at segment BC and segment AD. If we take a look at the slope of both of those segments, their slopes are equal to 0. Next, let's take a look at segment AB and segment CD. If we take a look at the rise and the run, or the change in Y and the change in X of segment AB, it's 2/1. If we do the same for segment CD, again, the change in Y is 2 and the change in X is 1. So we can also say that the slope of segment AB is equal to 2 and the slope of segment CD is also equal to 2. By doing this, we have shown that opposite sides are parallel because they have the same slope, and this verifies that the quadrilateral is a parallelogram. The diagonals in a quadrilateral are segments that connect opposite vertices. Use a straight edge, which would be just a ruler, to draw in diagonals AC and BD. We're going to find the equation of each diagonal, and also we are going to decide if the diagonals are perpendicular. Let's first take a look at diagonal BD. To find the equation of this diagonal, we need the slope and the y-intercept. The slope of this diagonal is its change in y over its change in x. To go from point B to point D, we need to go down 2 and over 2. The slope would be -2 over +2, which simplifies to a -1. To find the y-intercept, I'm going to use the equation y equals mx plus b. I know the slope, and I can use either the coordinates for point B or point D to help me solve for my y-intercept. I'm going to use the coordinates from point B. My y value is 3. My slope is -1 times the x value of 2 plus b. When we solve this equation, we will find that the y-intercept is equal to 5. The equation then for diagonal BD is y equals a -x plus 5. I would like you to stop the video now and use a similar process to find the equation of diagonal AC. You should have found the equation of diagonal AC to be y equals 1/2 x plus 1/2. The question that was asked was, are the diagonals perpendicular? In order for segments or lines to be perpendicular, their slopes must be opposite reciprocals. Opposite meaning opposite signs, positive and negative. Reciprocals meaning the fractions are flipped. If we take a look at segments BD and AC, BD has a slope of -1. AC has a slope of positive 1/2. These slopes are opposite signs, but they are not reciprocals of each other. Therefore, the diagonals are not perpendicular. We're going to further investigate properties of parallelograms by using the same figure as in the last problem, along with its diagonal BD. Take a look at the two triangles, triangle ABD and triangle CBD, that are formed in this figure. Using only the definition of a parallelogram, meaning that opposite sides are parallel as you're given information, why must these triangles be congruent? We're going to construct a flowchart proof to prove that the triangles are congruent to each other. If our given information is that ABCD is a parallelogram, that means the only thing we can use in our given is the fact that opposite sides are parallel. So we know that segment BC would have to be parallel to segment AD. We would also know that segment AB is parallel to segment CD. That's the only information we know given that we have a parallelogram. What we want to do next is see how we can use that given information to help us conclude other things about the figure. Because we have parallel lines, the first thing we should be thinking about is alternate interior angles. For example, because of the top and the bottom parallel lines, we know that angles 1 and 2 must be congruent to each other. Because of the parallel lines on the left and the right, we know that alternate interior angles 3 and 4 will be congruent to each other. And then, of course, we'll work in our shared side in the middle, and we're going to be able to say that these triangles are congruent to each other by angle, side, angle. Let's write up that proof. Now that we know the triangles are congruent, there are some conclusions we can make. What can we conclude about the measure of angle A and the measure of angle C? Well, because they are corresponding parts of congruent figures, we can say they are congruent to each other. What can we conclude about the length of AB and the length of DC? Again, because they are corresponding parts of congruent figures, we know that their lengths must be equal. And finally, what can we conclude about opposite sides AD and BC? Again, we know they are equal in measure because corresponding parts of congruent figures are congruent. Because of congruent figures, we know that in all parallelograms, opposite angles are going to be congruent and opposite sides will also be congruent. Our final topic for this lesson will be midpoints. The midpoint of a line segment is the point that divides the segment into two equal parts. The first thing we're going to do is graph 2 points P and Q. Point P has a coordinate of 0, 3. And point Q is going to have a coordinate of 9, 8. It's a typo on my sheet, but it's correct on your worksheet. And we're going to find the midpoint of segment PQ. The way that we're going to do this is by using the slope of the segment. The slope of segment PQ has a change in y of 8 and a change in x of 6. If the slope is 8 over 6, this tells us to get from one point to the next, we need to go up 8 units and over 6 units. If we want to go to the midpoint, we need to go half of that distance. This means to find the midpoint of segment PQ, we can start at point P and go up 4 units and over 3 units. Again, to find the midpoint, we need to use half the distance that the slope tells us to travel. So that means the midpoint of segment PQ is the coordinate 6, 4. To verify that segment PM is the same length as segment MQ, we're going to use Pythagorean theorem. Because we're using slope triangles, we just created right triangles. Each of those slope triangles has one leg that's length 4, another of length 3, and if we apply the Pythagorean theorem, we will find that the hypotenuse is equal to 5. Both of those mini slope triangles have the same dimensions, so they have the same hypotenuse length. What I'd like you to do now is work through the following practice problems. Our lesson on Wednesday will start with a discussion of these problems and their answers. All of the work that you did on this guided notes worksheet and all of the work you will do for these practice problems will be part of your class notes for the beginning of Chapter 7. You should put these notes in your math binder in your notes section. Remember that I have student support sessions scheduled on Tuesday, Wednesday, and Thursday this week, and the schedules for these are posted in Google Classroom. I am also able to meet with students individually by appointment on Friday this week. Please refer to my schedule for these support sessions and let me know if you have any questions.